Alright, so introduction to the tangent line. So far, you've had experience finding the secant line, which can be a good approximation to the tangent line, but it's not precisely exact. So our learning target today is I can define the tangent line and find the slope of the tangent line for any function. Alright, so we're going to take a look back into our original function that we were studying, y equals x squared right here, basic parabola. And we're going to be trying to find the tangent line at x equals 1. So right here at this point right here. Our goal is to find the equation of this purple line that's touching the graph at exactly 1 point at x equals 1, or at 1 comma 1. So the secant line we found was not a good enough approximation, right? You can get really, really close and choose points closer and closer to 1 comma 1, but you're not going to get an exact, right? We need to get more precise to find our tangent line. And then as a reminder, this green line that I have right here, that's your secant line, right? So you notice how the secant line, right? It's a good approximation, but it won't give you the exact purple line or the exact tangent line right here. This means that we need to make our slope more exact and precise. Basically, if our slope is more precise, then we will be able to find the whole equation of the line because we already have a point, 1 comma 1, and then we need a slope. We have everything we need to find the equation of the line. So that's why the slope here is super important. So something to think about at this point is how can we make a better approximation and how can we make the slope more precise? We can start by choosing our second point to be closer to the point 1 comma 1. So we've done this before when we're making better approximations of the secant line to the tangent line. We chose like 1.0001 and we're getting closer and closer to 1. If I choose my second point to be closer to 1 comma 1, visually you can see that the secant line approximates the tangent line better. Of course, you could draw the visual that you see right here above, but basically, if this second point right here, if I make it closer and closer to 1 comma 1, it will eventually become this tangent line. So then, great, that's good for approximations, but what is the exact definition of the tangent line slope? Okay, in calculus, we focus a lot on the tangent line slope for many practical reasons that you're going to see later on this course. For one thing, though, what I could give you as a good example is what it's used for. For example, if you're finding like the average velocity of a car, we know how to find the average, but what if I want to know the exact velocity of a car that's driving? Like at 2 seconds, exactly what is the speed of the car? Basically, to find the slope at exactly 1 point is going to give me that answer. So that's a practical reason of how we use these. In calculus, we do call the tangent line slope the derivative. Recall the slope of the tangent line used this formula. By the way, there's going to be many variations, but this is the one that we used to calculate from before. So we used change in y over the change in x. That's the slope formula. We start to define the formal definition of the tangent slope by first fixing our first point. What I mean by fixing the first point is we hold our first point, 1 comma 1, constant. And what I'm going to do now is I'm going to take my second point and I'm going to move it closer. So that means I have to make, in order to move the second point, I have to make the second point arbitrary. Now let me show you what I mean by putting it on the graph right here. So here's my first point, 1 comma 1. That's the thing I'm going to hold still, constant. My second point, so that I could move it, I'm going to call it arbitrary. What I mean by that is instead of like some comma number, something comma something, what I'm going to call it is x comma x squared, where x is my input and my output is my y, x squared. That comes from the function right here, see? X and then x squared, so x comma y. This makes the point arbitrary. What my goal is, I'm going to take this point and I'm going to move it so that essentially it's on top of this point to give me that tangent line slope. So here in the yellow is what I want, right? So I'm going to take this point, I'm going to move it closer so that I get this yellow line, which is my tangent. Great. So here are the 2 points that I now have. I have 1 comma 1, and then I have the arbitrary second point, x comma x squared. So to find the slope of these 2 points, I do change in y over the change in x. Remember, I color-coded it so you could see what I'm doing here. So it's y2 minus y1 all over x2, x1, x2 all over x1, which is shown right here. So that's the slope formula. Cool. So that's the slope of this right here, right? Between these 2 points. But if I want this point to move to this point, what I'm going to use is something from last semester or something from last time, which is a limit. If I put a limit in front of this expression and I say the limit as x approaches, and I want x to approach 1 because the x that I want is 1. So the limit that I'm going to make this approach to is 1. If I make this have a limit in front of it, I'm going to make this point approach this point. And then the limit will give me the slope of the tangent line. This is what that looks like right here. So to move that second point closer, we use a limit. So now I have this expression. So great. Now what I got to do is I find the limit of this expression, and that's going to tell me the slope of the tangent line. So the slope of the tangent line at 1 comma 1 is, well, let's use some math. Cool. It looks like if I plug in 1 first off, right, I'm going to get division by 0, which is not okay. So that means what I'm going to do is I'm going to try to factor out the top. Now, you can factor it using the box method, or you can remember that when you have like x squared minus some number squared, like 1 squared, which is 1, that's just going to become x plus 1 times x minus 1. This will cancel out. Then you'll have the limit as x approaches 1 of x plus 1. Now I'm able to plug in 1, and that's going to give me the slope of the tangent line finally. It's 2. Great. So we have the slope of the tangent line. Now what we got to do is find the equation. The equation will be straightforward because we have our point. The point is 1 comma 1, and we have our slope, which is 2. So there's our slope. Here's our coordinate point that I'm substituting in. And now I'm going to solve for b so I could get my equation. So there we go. The equation of the tangent line is y equals 2x minus 1. So we found it finally. And this is not an approximation. This is exactly the tangent line. Let's go ahead and do some examples. Well, the formal definition of the tangent line, by the way, has 2 variations. You are expected to know both. But for now, we've been working on this one right here. The limit as x approaches a of f of x minus f of a all over x minus a. So like the f of x parts and the x parts is basically the arbitrary part. This a part is basically the point that we chose. In our case, we chose 1 comma 1. The second definition that I do want you to have exposure to already is this one here. These two actually mean the same thing. This one just uses a different way to express it. We're going to see this later on, but this kind of means the same thing where you're taking a point and moving it closer to another. This is what these definitions are doing. Both of these definitions are the definition of the slope of the tangent line. Alright, so to find the slope of the tangent line, the definition is basically is you pick your point that you want, or you're given the point, right? Usually like at a certain point. And then what you do is you got to make one point arbitrary. So that's the definition. So let's take a look at an example. Find the derivative of f of x equals 3x squared minus 1 at x equals 2. So basically the point that I need to hold still is going to be 2 comma something. So I'm going to take the 2 and I'm going to plug it in here to find out what that something is. So 2 squared is 4 times 3 is 12 minus 1 is 11. So the point that's going to be constant is 2 comma 11. Now to get that second point, which is the arbitrary point, what you got to do is always x comma y. The y is already kind of just given to you. This is your arbitrary point that's going to move closer to this point. So essentially, I'm not really using this definition. I'm kind of just constructing this and making sense of it, to be honest, is what I'm doing. Alright, so I have my two things. Remember, what I'm trying to do is find the slope of these two things. And then in front of the slope of these two things, I have to put the limit as x approaches 2, because that's where I want the tangent line to be at. So here we go. The slope of the tangent line is going to be the limit as x approaches 2 of y2 minus y1 right here. So notice, yeah, no, it's perfect. And then we have x minus 2. Great. I was just double checking if I had any double negatives, but that's not happening here, so you don't have to worry about that. Cool. Great. Let's go ahead and simplify the top. So I have negative 1 minus 11. It's negative 12. Cool. So now, usually what would end up happening is you plug in the limit that you want. The problem is, again, we're encountering that division by 0. So what we have to do now is some algebra so that we don't get division by 0. Here's what I'm going to do. At the top right here, I notice there's a 3, and I notice that 3 is a multiple of 12. So what I'm going to do is I'm going to factor out the 3 from this top expression. If I do that, I think I'm going to get something that I can factor and then cancel the x minus 2 at the bottom. Good. So x squared minus 4, this right here will factor into x plus 2 times x minus 2 while keeping the 3 on the outside. Great. So once I broke it down like that, I can cancel these two right here, the ones that are the same. Then what I'm left over with is this. Awesome. It looks like I don't have division by 0 anymore, so I can now plug in that 2. So I plug in the 2. I'm going to get 3 times 2 plus 2, which is basically 3 times 4. The slope of the tangent line is 12. Once I have the slope, I could go ahead and find the equation of the tangent line. So here's my slope. The point is 2, 11, so x, y. That means y is 11, x is 2. Substitute that in. Great. When I solve for b, it looks like I get negative 13, so 12 minus 11, yeah. Cool. Here's the equation of the tangent line. There we go. So again, when I'm doing the finding the slope of the tangent line, I am using this definition, but what I'm doing is actually just constructing and then taking the limit of the point that I want is what I'm doing. Let's do one more example, and then you can head off to trying these out on your own. Finding the derivative of this long function at x equals negative 2. Now here we go. So the first point that's going to be held constant is the point that when you plug in negative 2, you get your output. So if I plug in negative 2 into here and do some math, you should get negative 2 comma negative 11. Double check that for me. And then what you have is your second point. The point that's going to move is going to be x comma then the function itself, because that's like x comma y. All right, so we have our two things. We're going to do change in y over the change in x, and then I'm going to take the limit as x approaches negative 2, because that's the point that I want. So here's my construction. So y2 minus y1. Ooh, look, a double negative right here. Then we have x minus, so we have x2 minus x1. Again, because we have a double negative right here, be very careful. These are going to become a plus. Okay, so let's go ahead and simplify. Like terms, negative 7 plus 11. I think that gives you 4. Cool. Now we're going to go ahead and try to factor this so we could cancel some stuff out and so that I could be able to plug in negative 2. Now this one here, before you try to do a box method, make sure that you pull out the common multiple. The common multiple here looks like it's 2. You have to first pull that out. And then I apologize, I really don't know why this stayed small, but anyway. Then you could factor out the stuff in the inside. So using the box method, you have to find out what multiplies to give you 2, but adds to give you 3. Luckily, 2 times 1 gives me 2, and 2 plus 1 gives me 3. So that one's kind of straightforward. That factors into this. And again, if you want me to show you how to do box for that, just as a reminder, feel free to let me know. I'm happy to do that on the board. But here we go. X plus 2's cancel out. Now I'll be able to plug in the negative 2 in right here. So it's going to be negative 2 plus 1. Negative 2 plus 1 is negative 1 times positive 2 on the outside. It looks like the slope of the tangent line right here is negative 2. I'm going to go ahead and take that negative 2, plug it into my y equals mx plus b equation. Then I'm going to take the point, negative 2 comma negative 1, plug it in here to find the b. And then, sorry if stuff is in the way, but what I get when I solve for b is negative 15. So the equation of the tangent line for this right here is this. This right here is how you find the derivative, aka slope of the tangent line, the exact slope at a point for any function. Again, you can apply this to finding, if you have a velocity graph, you can find the exact velocity or the exact acceleration at an exact point. Things like that is how we'll apply this instead of just looking at averages. All right.